If you don't mind, we could start. I mean, it's 1:05. People are still coming, which I don't like to see so much. I mean, of course, every now and then it happens that you come late, but it shouldn't be regular. So try to commit to coming here for 1 o'clock, and also to try and not chat when I would like to start telling you things. Thank you. Yes, the other day in my office, I was just walking at my desk like this, and then in the corner I saw a big box and two big boxes, well, small boxes. And what I found was linear programming books in those boxes. But then, of course, I wouldn't carry them all the way here, so you won't get anything. So I thought, and then Philip said that, well, he kindly offered to take them to his lecture in John Bolton this afternoon, so you should, unless he forgets, which is possible, because I would definitely forget if it was his books. So he should bring these linear programming little things. Okay. So I think I would like to keep the noise level down, not only at 1 o'clock, but also at 1:05 and 1:10, and all times between, and all the way until 2. So if you have something really urgent to say that is related to what we're doing here, then don't be shy and tell me and tell everyone. If you have something really urgent to say that is not at all related to what we do in these lectures, then just go away and keep saying it somewhere else, because otherwise it's disturbing the people who are here to learn something. Thank you. So that's like a warning. The next time it's a yellow card, and that's 10 minutes in the sin bin. Right, so what did we do last week? What did we do? Yes, we were drawing things in the plane, linear inequalities, and I don't have the... Forgot the laser, so I apologize. So I'll have to be pointing here. So we had these three inequalities given as some kind of linear functions of two variables. And then we have two non-negativity inequalities. And we said that each of them defines a half plane, so a straight line, and one half of the plane is the points that satisfy this constraint, and the other half don't. And then we drew the picture, and then in the picture we found the point that has the best value of the objective, which is the 15x1 plus 20x2. Okay, so that's what we did. And then we said that it's not a very good method. Why? Aha, so one of the reasons is that we can only really draw it in the plane if we have two decision variables. If we start having 100,000 decision variables, then it becomes rather unhelpful to draw things in the plane. And so what I promised you was something that's called the simplex method. Okay. Why is it called the simplex method? I won't tell you yet, but I might tell you at some point. Okay. So yeah, so let's just do the simplex method, and let's not think about why it's called the simplex method for now. And maybe if you ask me again sometime, then I'll tell you what it is, why it's called that. Okay, so what does the simplex method do? Okay, the simplex method, what does it do? How do I? Okay. So what do I want? Okay, I want to call these these constraints star, like this. Okay, and so star is all these constraints. And what I want to do is something that I told you last week already, but it's good to recall that we said that any triple I've already messed up. I want to call this Z. That's what we did last week, and I want this to be included in the star. Sorry about that. It's not a good start, but there you go. So any triple, let's say x1 dashed x2 dashed z dashed, that satisfies all these three constraints is called, do you remember what it was called? I said it last week already. You probably don't. That's why I'm saying it again. So it's called a feasible solution. Of the LP, let's call it star. Okay, feasible solution. Well, it's a technical thing. Pardon? What dashes? Oh. Yeah, so that's a bit of a, I don't really know. Okay, so if you take x1 dashed, which and you plug it in for x1, and you take x2 dashed. So I'm trying to differentiate between the decision variables in the formulation and some concrete values of numbers, but they're, yeah, so they're concrete numbers, but they're any numbers, and that's why I use letters for them. Yeah, so they're okay. So this, yeah, I probably wouldn't have to do it, but so I try to, yes. So if you plug in, so if you substitute x1 dash for x1 and x2 dash for x2 and z dash for z in the system, then if everything is satisfied, then I say that these three numbers are a feasible solution. Okay, so for example, if you asked, well, if x1 is 3 and x2 is 2 and z is 65, then this is a feasible solution. Okay. Does it make sense? Okay, so, well, that's maths. In maths, you use letters for things, and that's what allows you to do anything in math. Okay, so we know what this is. Now, what the simplex method does is it doesn't like inequalities. So the simplex method needs equations everywhere. Well, it kind of tolerates some inequalities. It tolerates this x1 and x2 greater than or equal to 0. But it doesn't tolerate 3x1 plus 2x2 is less than or equal to 160. It just doesn't like these. And so what it does is it transforms all these, the top three inequalities, into equations. Okay, so the simplex method needs equations to work. Otherwise, it doesn't work. And so what it's going to do is, instead of having just these variables x1, x2, and the objective z, it takes three new variables, one for each of the constraints, and these are called the slack variables. So it introduces what's called slack variables. No, that's not the way to spell introduce. Introduces slack variables. And in this, and there are as many slack variables as there are constraints. So in this case, we have, I'll call them S1, S2, S3. And what it does is it rewrites star as equations. So we'll rewrite it like this. Maximize Z. Okay, that remains. Now, subject to the following constraint. So we'll come back to the Z in a second. But the first constraint is going to be 3x1 plus 2x2 plus S1 is equal to 160. Okay. The second constraint is going to be x1 plus 4x2 plus S2 is equal to 200. The third constraint is going to be half of x1 plus 1/2 x2 plus S3. I think you see the pattern here. Is equal to 31. No, you don't see the pattern because it's hiding. Yeah. Ah, that's a great question. I'll tell you in a second. I think, yeah, I mean, yes, you're right, but I'll tell everybody else in a second. I'll ask you again. Because I haven't, I mean, yes. So yeah, so I haven't finished yet. Okay, so the next one is that Z, take away 15x1, take away 20x2 is equal to what? Zero, yes, because Z is 15x1 plus 20x2. And then there are constraints that say that x1 and x2 and s1 and s2 and s3 are greater than or equal to 0. Okay, ask your question again, please, Jake.
Just whether or not the slack variable some unknown value that allows the inequality to be satisfied.
Yes. The slack variables are the value that allows these to be satisfied. I forgot my laser pointer. So if you look at this, S1. This S1 gives you the difference between the expression 3x1 plus 2x2 and 160. Well, here it is. Yeah. So it tells you how much is missing when you calculate your 3x1 plus 2x2 there. How much is missing to get 160? So it's the difference between 160 and the left-hand side of the constraint. Now, here I want that difference to be non-negative. Okay? So what I want is that 3x1 plus 2x2, I have to add something non-negative to get 160. And that is the same thing as requiring, as I did at the top, that 3x1 plus 2x2 is not more than 160. Does that make sense? Yeah. So instead of just writing an inequality like I did at the top, what I do is I write an equation where I add the difference between the right-hand side and the left-hand side in the original inequality, and I call it a slack variable. So if you think of why it's called a slack variable, so if you think of like the 3x1 plus 2x2 can be more than 160, so you take a row that's 160 long, okay, and then the 3x1 and 2x2, whatever, that is on the row. So it can't go more than 160, and if it's less than 160, then there's slack in the row. Okay. So that's why it's called slack variables. Does it hold if which inequality was? No, none of the inequalities is strict. Okay, that's a good point. So in linear programming, we don't do strict inequalities. Yeah. So any linear programming problem always has inequalities less than or equal to or greater than or equal to. The equal to, we don't leave out. Why? Okay, you have too many questions. We're not going to get anywhere, but that's good. I mean, I like it. So it's kind of okay. So when you go back to the geometry, which is on the cover, right? Then less than or equal to means that it's in the half plane, including the boundary, including the straight line that is the boundary of the half plane. And you want to include the boundaries in the feasible region, because otherwise you wouldn't get an optimal solution, because you could get arbitrarily close to the boundary, but you'd never, it would be some kind of a closed versus open set thing. So anyway, you always want non-strict inequalities. Okay, so I'll call this heart. So I want to claim, what I've kind of argued is that, even though you don't know what star was because it's disappeared now, I want to claim that solving heart is equivalent to solving the original problem, star. So in fact, there's more to it. And that is because of what we've just been arguing. So if, because there is a correspondence between the feasible solutions of star and the feasible solutions of heart. Okay, so if you have 3, 2, 65, that was the example, is a feasible solution of star, that's what we said. And then from there, you can go to 3, 2, where do I put the 65? I'll put it at the end. Okay, so what does S1 have to be for 3 and 2? So if X1 is 3, X2 is 2, what does S1 have to be in order to satisfy that equation? Well, we get 13, so 147. 3 times 3 is 9, plus 2 times 2, that's 4, that's 13. So we need 147. So this is x1, x2, s1, 11, 189 for s2, and 2.5. Okay, so this is a feasible solution. Hard. Does that make sense? Is that clear how I came up with that? Well, x1 has to be the same, and x2 has to be the same, and z also has to be the same. And the s1, s2, s3 is exactly what I just said, namely the difference between what you get in the expression and the right-hand side of the constraint. Okay, so like this, you go one way, but you can also go the other way, because if you just forget the values of the slack variables, then you get a feasible solution of the original problem. Okay, so in other words, we have the exact same feasible solutions in the x1, x2, and z variables, and therefore finding x1 and x2 that is the best for star is the same as finding the best x1, x2, s1, s2, and s3, and z for heart. Okay? Hope that makes sense. So that's what we do first thing in the simplex method. Introduce slack variables and change inequalities into equations. Now, the goal is to find the maximum z. And so if we're trying to find the maximum z, we called the solution that achieves this maximum an optimal solution. Okay, so I'll repeat it as a definition. And I say that a feasible solution that maximizes the value of the objective z among all feasible solutions is called an optimal solution. The reason I'm saying an optimal solution rather than the optimal solution is that, as we briefly saw last week, there could be several optimal solutions that have the same value of the objective and are all feasible. So we usually speak of an optimal solution rather than the optimal solution. And that's our goal, actually, is to find one. So goal, find an optimal solution. An optimal solution, oh, I keep missing this. I should draw a line somewhere here. And not right now. Oh, it's caused damage to university property. And an optimal solution of what? Well, of heart, because once we found a feasible, an optimal solution of heart, that will automatically give us the star that we were originally interested in. Okay, so this is what we want to do now. Go away. It won't all fit. I want everything to be there, but it just won't. Okay. Now you may notice there is a particular look at all the we have 4 equations. There's one special thing about these 4 equations. Well, there are probably more special things, but one special thing that I have in mind is that each of these equations has one variable that in it is with coefficient 1. So there is 1 times S1, 1 times S2, 1 times S3, and 1 times Z. And that variable does not appear in any other equation. Okay, see that? So S1 only appears in the first equation, and it has coefficient 1, because there's 1 times S1, not 2 or 3 or 4. And S2 in the second equation, S3 in the third, and Z in the fourth. And these variables are called basic variables. So there is a special property of Hart, which I call the simplex property. And that is that every equation contains a variable with coefficient 1, which does not appear in any other equation. Okay. And such a variable is called basic variable. Okay, and all these basic variables form a basis. Now, sorry? Affect the pieces. Vector basis. No, it's just called a basis. It's got nothing to do with vectors. Well, it has to do with vectors, but it has to do with matrices. You'll see later. He's pushing me to... I should probably just stop doing what I've prepared and start talking to completely different. Anyway, what I need to. So what are the basic variables here? S1, S2, S3, Z. What are the variables x1 and x2 called? Just variables? Well, they're called non-basic variables. Okay, so what's important about this is, well, many things are important about this. But another thing is that there is a particular feasible solution that I want to associate with every system like this with the simplex property. Okay, the system with the simplex property, I'll call it a simplex tableau. So system of equations with the simplex property is called a simplex tableau. Okay, and then what there is every simplex tableau has a special feasible solution, which is called the basic feasible solution. So to every Simplex tableau is associated a basic feasible solution and the basic feasible solution has the property that oh, I'm running out of paper. That has the property that all the non-basic variables are set to 0. Okay, so all the non-basic variables are 0 in that basic feasible solution. The question is, what are the remaining? What are the basic variables in that basic feasible solution? Well, it just won't fit. I need bigger. Anyway, I need bigger things. So if all the non-basic variables, well, all the non-basic variables are 0. So that's the x1 and x2. What is S1? If x1 and x2 is 0, what is S1? 160. What is S2? What is S3? What is Z? Aha. So that's a basic feasible solution which is associated with this simplex tableau. The non-basic variables are 0, and the basic variables have to take their values from the right-hand side, because if you plug in zeros for all the non-basic variables, that's everything that is left in that in each of the equations is just one basic variable. Okay, so so the basic variables take the values of the corresponding, only one L, take the values of the corresponding right-hand sides. So that's what it is. Okay, now I need more stuff. Is this the best possible basic feasible solution? No? Why not? Because we have a better basis. For example, yeah, so if you see, there is minus 15 and minus 20. So any feasible solution will satisfy that z minus 15x1 minus 20x2 is 0. But x1 and x2 are non-basic, so they have to be 0 in the basic feasible solution. But that means that z can only be 0. But if we increased x2 a little bit, okay, z would have to increase for the last equation to be satisfied. Yes, so if x2 becomes positive, then z has to be larger as well. If x1 becomes positive, then z has to be larger as well. because it has to satisfy that last equation there. So it makes sense to make x1 or x2 to put it into the basis, because like that we can hope that it's going to be positive rather than 0. And so if x1 or x2 becomes positive because it's in the basis, then the solution, well, z will have to increase. Do you agree? So which one shall I put into the basis, x1 or x2? x1? Who wants x1 in the basis? Who wants x2 in the basis? There's more votes for x1, so we can do x1. No, it's because you said x1. In fact, yeah. Okay, so put x1 into the basis. Now, I want a new simplex tableau with a new basis. How am I going to do that? Well, what we get is, again, we get maximize z, and now we need to redo the system of equations so that x1 would only appear in x1 would only appear in one of the equations. Okay, now the thing is, we have to work out, right, so there is a bit of a problem, right? So how many basic variables can we have? We can only have 4, because there are only 4 equations. So we have to remove one of the variables that is currently in the basis. We have to take it out of the basis. Well, we don't want to take z out of the basis, because z is the objective, and it always has to stay basic, because we don't want the objective to be 0. That's not good. And so we have to work out which of the variables to take out of the basis. And this is done like this. So what to remove? So the first equation says that S1 is 160 minus 3x1 minus 2x2. Now, in the next basis, x1 will be in the basis, but x2 won't. We leave x2 as non-basic. So this is going to be 160 minus 3x1, yeah, because x2 remains non-basic. And this should be greater than or equal to 0. Because S1 has to be greater than or equal to 0. We can see that here. And so what this gives us is the inequality that x1 must be less than or equal to 160 divided by 3. Okay? So that was the first. When we look at the second constraint, we get S2 equals 200 minus x1 minus 4x2. So, well, again, this is 200 minus x1, which should be greater than or equal to 0, and therefore x1 should be less than or equal to 200. And the third one, the third equation tells us that S3 is 31 minus 1/2 of x1, which is greater than or equal to 0, And therefore, x1 should be less than or equal to 62. So which of these three bounds, got three bounds, 160 divided by 3, 163rd, 262. Which of these three numbers is the most constraining one? The last one? Why is it the last one? The last one is in the middle. I think it's the first one. So the first one is the smallest of these three numbers. 160, well, 62 times 3 is more than 160. So 163rd is less than 62. So this one is, that's the toughest one to satisfy for x1. Okay? So this is the most constraining constraint. So you can think of it as you're increasing x1, and in order for all these three equations to be satisfied, s1 and s2 and s3 have to start decreasing. Okay? If x1 is going up, s1, s2, s3 have to go down, because that goes up, that has to go down in order to, x2 doesn't change. So in order to stay a sum of 160, then that has to happen. Now, this 160 divided by 3, that's the most constraining one. So S1, as you keep increasing x1, S1 is going to be the first to hit 0. And so it has to be S1 that leaves the basis and becomes non-basic. Okay, so from this, because S1 was here, so that, most constraining, says that S1 leaves the basis. Oh, and I'm out of screen again. Okay, that's how it works. So S1 leaves the basis, and now the thing I started, maximize Z, I can actually finish that. So I'll restart. Okay, so what we get is maximize Z. Now, okay, so now we had these four basic variables, S1, S2, S3, and Z, and each of them somehow owned an equation. Okay, so S1 is now going to be released from the basis, so it won't own an equation anymore. So the first equation will be free, and so that's the equation that X1 is going to get. Yeah, so X1 gets the first equation, and it has to have a coefficient of 1 in that first equation. And so because it needs this coefficient of 1, then the easiest thing to achieve this is to divide the whole first equation by 3. Okay, so if I divide the first equation by 3, I get x1 plus 2/3 x2 plus 1/3 s1 equals 160 divided by 3. Okay, do you agree? Go away. Now, x1 should not be contained in any other of the three equations. So the easiest way to do this is to do a suitable row reduction, because we want to keep an equivalent system of equations. So by doing row reductions, we can achieve this. Okay, so the row reduction that I'm doing here is I take this equation, the new one. I think I should be calling them names. So I take the new one, and I subtract it from the second equation. Okay. So the second equation was x1. I'm taking away x1, so there won't be an x1 there. 4x2 minus 2/3 of x2. 4 minus 2/3. Well, you can work out yourselves. x2. Then I didn't have any s1, and I'm taking away 1/3 of s1, so I'm getting minus 1/3 s1. And then I had s2, and I'm not taking away any s2, so s2 remains there. And there was no s3. And I have 200, and I'm taking away 160 thirds, so I get this. Is that clear? Yeah, well reduction to get rid of x1. And for the third equation, I have to take away 1/2 of this. So what am I getting? No x1. There was half x1. I'm taking half away. There was half x2. And I'm taking away 1/3. Because I'm taking away half of the 2/3 there. And there was no s1. I'm taking away 1/6 of s1. There's no s2, and s3 remains there. And I'm taking away 31 minus 160 divided by 6 there. Are you still following, or is that okay? I hope so. Now the remaining one, last equation, I have to get rid of x1, so I take 5 times, for example, I could take 15 times this row, this equation, or 5 times this equation. That's the same, and I added to the z. So z, and I had minus 15. I'm adding 15, so I had no x1. I had minus 20, I'm adding 10, so I get minus 10x2. I had no s1, I'm adding 5, so I get 5s1. I had no s2, I'm not adding anything. I had no s3, I'm not adding anything. I had 0, I'm adding 5, so what I'm getting is 800. So what we get is a new simplex tableau. Now, Z is 800 in the basic feasible solution. Okay, so we've improved the objective. The question is this an optimal solution now? Well, the basic feasible solution, can you see what it is? X1 is 163rd. X2 is 0 because it's non-basic. S1 is 0 because it's non-basic. S2 is, well, you have to work that out. I was too lazy to do that in my head. And S3 is 31 minus that. Yeah. And the Z is 800. So that's a new basic feasible solution. The objective has improved, but is it the best possible? Yes? No? Well, you don't know, but it isn't. The reason it isn't is, who wants to know? Okay, is that there is minus 10. Okay, so that means that if we insert x2 into the basis, then we can still improve. Well, by something. And that's what you can do at home, or so, and then we'll look at it next week.